Tonight drift into the quiet side of the universe. Far beyond familiar skies, a nearby star system holds faint gradients, thin rings of dust and worlds that reveal themselves only through subtle changes in light. In this sleep documentary journey, the story moves from a planet's soft phase glow to the vast boundary where stellar wind meets interstellar space. If this kind of calm science storytelling helps you unwind tap, like to support the channel, subscribe for more long-form cosmic sleep films and turn on notifications so the next voyage finds you. The nearest stellar system hides its smallest details behind its own light. In that region, warmth carried in infrared light offers a cleaner trail than visible brightness. Alpha Centauri sits about 4 light-years away, a span equal to 4 Earth orbits measured in light travel time. Nearness sounds like clarity. Nearness also makes the glare sharper and the challenge more intimate. 2 bright stellar disks sit close in the sky. Their edges soften into a pale wash. A faint third star sits farther out, dimmer and redder. The scene resembles a bright moon in thin mist where nearby stars fade even though the air feels clear. Light behaves as a wave. Even without dust, a bright source spreads into rings and a shallow halo. The halo is not a solid thing. It is a gradient of brightness that falls away slowly. Any faint companion must climb out of that slope before it can be seen as separate. The first quiet unlock appears here. Distance is not the only obstacle. Contrast is the obstacle. Contrast means difference between bright and faint light. A planet can be close and still disappear. It can be present and still be swallowed by the star's own spill of light. The system's brightness sets a floor. Anything below that floor blends into the glow like a pale pebble on a sunlit sandbank under moving water. The surface is there. The pattern of light hides it. In that layered brightness, the search shifts from sparkle to warmth. Infrared means light felt as warmth. A dark rock on a cold plain continues to release heat after sunset. The glow is faint, yet it carries information about what the rock is. In space, a planet also releases heat. Reflected starlight depends on angle and distance. Emitted warmth depends on temperature and surface and air. In infrared, the planet's own glow can matter more than its borrowed shine. This becomes a second unlock. A planet does not need to glitter to be found. It can simply be warmer than the darkness around it. The geometry changes. The star remains a bright core. Around it, a faint point can appear more steadily, because it is not fighting the same kind of glare. The halo still exists. Its shape still matters. Yet the balance can tilt. Heat stands out where reflected light fails. A thin ring of dust can also glow. A small cloud of grains can mimic a world if the grains sit at the right distance. The boundary between planet and dust is not a line. It is a spectrum of possibilities. The sky over Alpha Centauri is not empty space around 3 lights. It is a volume where material can orbit, collide, and spread into bands. A delicate veil can form and still remain almost invisible in ordinary light. In infrared, that veil can brighten like fog warmed by dawn. The edge of that fog is never sharp. It fades by layers. A denser lane looks like a soft ribbon. A thinner lane looks like a faint smear. The system's closeness magnifies these structures in angle, even when their true size remains enormous. A dust ring the size of a planetary orbit still appears as a tiny curve. Its glow competes with the halo's slope. A small payoff settles in. Closeness gives larger apparent separation. Closeness also gives a more crowded field of competing glows. The search becomes a careful reading of gradients. A planet should hold a compact shape. Dust should spread into a thicker blur. That rule helps, yet it is never perfect. Dust clumps. Planets where haze is, light scatters. In that region, scattering is not an abstract idea. It is a physical redistribution of brightness. Grains redirect starlight. Gas bends and dims and colours it. Even empty space can carry stray light from the star's own rings of diffraction. The star's halo can carry ripples. Those ripples can imitate a faint dot. This is where the limit of observation arrives gently but firmly. The eye cannot separate the true object from the star's spill by brightness alone. The pattern is contaminated by the wave nature of light. The separation is limited by resolution, and resolution is limited by wavelength and aperture even in principle. A faint planet can hide inside a ring of glare. A dust knot can pretend to be a planet for many cycles. Heat does not solve every ambiguity. Warm dust at the right distance can glow like a small world. A thin atmosphere can smear a planet's edge and make it less point-like. The method relies on inference. It relies on shapes and colours and their changes with time. Inference has boundaries. A single snapshot cannot prove what the faint light is. It can suggest. It can narrow. It can mislead if the halo is not modelled with care. The system itself adds another complication. Alpha Centauri is not one star. It is a bright pair in a long mutual orbit plus a distant red companion. The bright pair's combined glare is not symmetric in all moments. Their separation changes, their overlap changes, the halo changes with that geometry. The light field is like two overlapping ripples on a pond where the pattern shifts as the sources shift. A faint object must be tracked across that moving interference. A slow rhythm replaces any urge for instant certainty. The faint point should shift position relative to the stars in a way that follows gravity. Dust should smear and brighten in a different cadence. Here another small unlock appears. Time becomes a filter. What remains coherent across months is more likely to be a compact body. What stretches and reshapes is more likely to be a cloud. Even then the distinction can blur. A planet with a thick haze can look soft. A narrow dust ring can look sharp. The boundary is negotiated by repeated geometry, not by a single dramatic reveal. The physical scene remains vivid. 3 stars sit in a shared neighbourhood of darkness. Around the brighter pair, a subtle sheen can trace a ring-like structure. The ring is not a metal band. It is a gradient of dust density, thicker in one arc and thinner in another. In infrared, warmer patches glow more strongly. The glow forms a faint crescent where grains face the stars. The shadowed side cools and dims. A planet would show a similar phase, yet its edge would be cleaner. Its motion would be steadier. Its warmth would follow a different balance between day and night. The scale shifts down to the smallest actors. A single grain absorbs a photon. It warms by a tiny amount. It re-radiates that energy as longer wavelength light. Countless grains do this together and a ring becomes visible. A planet's surface does the same, but with mountains and oceans of rock and ice shaping the emission. The scale then drifts outward again. Orbits span millions of kilometers. The whole system moves through the galaxy. The nearest neighbor is still far enough that light takes years to cross the gap. Within that calm distance, the main story of this first section settles. The nearest system is not a simple bright target. It is a bright foreground that must be peeled back by patience and by the quieter language of heat. The next section turns from light to motion and follows how 2 central stars reshape every stable path around them. A double star does not hold still long enough for the space around it to feel simple. In that region, gravity shifts its balance point as the pair circles, and stable paths must match that slow rhythm. The 2 bright stars loop around a shared centre, and their separation subtly changes. Their combined pull forms a landscape of invisible slopes. It resembles 2 neighbouring valleys with a low saddle ridge between them. Anything drifting near the saddle can slide toward either side. Anything deep inside one valley tends to stay captured. The first calm unlock follows. Stability is not a promise of stillness. Stability is a promise that small nudges do not grow. A small body can circle one star closely and ignore the other most of the time. Another body can circle both stars from farther out and treat them as one source of pull. Between those two styles lies a restless boundary where the tug alternates. The boundary has no hard wall. It has gradients like wind changing direction across a wide plain. A visual scene settles into view. Two bright disks hang close together. Around them, a thin, dim band of dust curves like a pale ribbon. The ribbon is not uniform. One arc looks slightly thicker. Another arc looks faint and laced. The thicker arc traces where grains linger. The thinner arc marks where grains are stirred and dispersed. Motion is not seen as speed. Motion is seen as shape that repeats. As the stars circle, their gravity paints gentle patterns into the dust. The patterns are broad and slow. They do not flash. They simply persist, then soften, then return. A second small unlock appears inside that dust. Gaps can mean influence. A clean lane inside a dusty band can point to repeated stirring. A stirred lane is not always a planet's work. In a binary system, the stars themselves can carve lanes by timing alone. When two pulls arrive in a regular cadence, the same parts of an orbit get nudged again and again. The word resonance fits here. Resonance is repeated tugs that add up over time. In plain terms, a swing rises higher when pushes arrive on beat. In this system, the beat comes from the binary motion. A small object can feel a push at the same orbital phase over many circuits. The pushes do not need to be strong. They only need to return with patience. That is why a clean gap can open without any single violent event. The gap is a quiet record of repeated timing. Physical detail anchors the idea. The dusty ribbon shows a soft inner edge. The edge is not sharp. It fades by layers as if dust density thins across a shoreline. Closer in grains warm and glow more. Farther out they cool and dim. The gradient is a thermometer drawn in space. It also becomes a map of where stable paths can exist. Too close to the bright pair, the gravity field changes too quickly across an orbit. Too far the field smooths, but the material can spread into broader rings. The system's long cycle matters. The bright pair takes about 80 years to complete a full dance. That span is like a human lifetime, long enough for a single tree to mature from seed to shade. Over that time, the valley and saddle pattern slowly rotates. Any stable path must survive not one moment, but many seasons of changing geometry. The third calm unlock arrives here. Short snapshots can mislead. A dust clump can look like a compact object if seen once. Over years, a true orbit draws a consistent track. A transient clump smears, shifts, and dissolves. Time acts like a gentle sieve. Coherent motion stays. Incoherent structure fades into the background glow. Another visual anchor drifts forward. Imagine a field of faint grains moving through a soft spotlight. Where their paths cross the glow thickens into a luminous braid. Where their paths diverge, the braid loosens into faint threads. The braid is not made of rope. It is made of repeated crossings in orbital phase. The threads never touch. They only align. A stable region appears as an orderly braid that returns. An unstable region appears as a frayed band that never quite repeats. The scale then shifts downward to the smallest causes. A single grain feels a tiny change in force as one star moves. The direction of pull tilts by a small angle. On the next circuit, the tilt returns, but not exactly. Over many circuits, the tilt can add or cancel. This is where intuition starts to strain. A simple picture of circles around a star breaks down. The true paths are not circles. They are loops that precess and wobble. Their boundaries depend on initial conditions that cannot be known perfectly. The limit of observation lives in that uncertainty. The exact starting position and velocity of a faint body cannot be measured with infinite precision at this distance. Small measurement errors can predictably grow when the region is near the saddle. Models can map zones of likely stability, yet the edge of the zone is fuzzy. The fuzziness comes from sensitivity, not from drama. It comes from the system's layered pulls and the finite clarity of any inferred position. Another small unlock settles with that limit. The presence of a fuzzy edge is itself information. It means the system contains a transition from orderly to irregular motion. It means there are regions where long-lived orbits are rare. It also means that any planet near that edge would leave subtle signatures. The signatures might appear as gaps that widen with time. They might appear as dust that gathers into arcs then disperses. They might appear as a compact warm point that shifts with a steady cadence across the changing glare. Each signature is modest. None is a single decisive stamp. The story remains calm because the physics is incremental. A final visual scene comes into focus. The two bright stars cast overlapping fields of light. Their halos merge into a shallow plateau of brightness. Within that plateau, a dim ring of material shows a faint shadowed notch where the glow dips. The notch is not black. It is simply less bright. It suggests a place where grains are repeatedly kicked into new paths. It suggests that gravity has carved a groove without carving a hole. The scale widens again beyond dust and beyond any single orbit. Over millions of years, the binary motion can reshape the distribution of small bodies again and again. Some grains collide and become finer. Some clump and become larger. Some are pushed inward to warmer lanes. Some drift outward to colder bands. The whole system evolves as a slow sculpture made by repetition. The next section turns away from the bright pair and toward the dimmer companion. In that quieter neighbourhood, closeness brings another kind of constraint, and day and night can become fixed patterns on a single world. A dim red star makes the closest orbits feel quietly permanent. In that region, tidal locking leaves one face of a world in lasting day and the other in lasting night. The red companion sits away from the brighter pair. Its visible glare is weaker. Comfortable warmth therefore lies nearer in. Nearer means stronger tides. Tides are gentle stretches inside rock and ice. The near side is pulled slightly more than the far side. That small difference repeats without pause. It raises a low bulge and drags it. Friction turns that flexing into internal heat. Rotation loses energy first. The spin slows until it matches the orbit. Tidal locking means one side always faces the star. The idea sounds simple, yet the outcome is a whole climate pattern. A small payoff settles early. A planet does not need seasons of tilt to have strong contrasts. Permanent lighting alone can create them. The physical scene becomes stark and slow. One hemisphere holds a steady noon. The opposite hemisphere holds a steady midnight. Between them lies a narrow belt where light arrives at a slant. The belt is not a razor edge. It is a gradient of illumination. The ground brightens, then fades, then falls into shadow. A thin ring of twilight wraps the globe like a narrow sash. In that sash, shadows are long. Ridges cast stretched silhouettes. Those silhouettes keep the same orientation. On the night side, cold settles into basins. Frost can thicken into a matte crust. Ice can extend in broad lobes that stop at a thermal boundary. The boundary looks like a coastline, yet it's made of temperature. Another small payoff arrives. The most gentle conditions can sit on the border, not at the centre of day. Heat transport becomes the next checkpoint. Warmth moves through air, through liquids, and through the ground. Even without oceans, an atmosphere can carry energy from day to night. Air near the brightest point warms and expands. It rises and spreads outward at altitude. It cools as it flows away from the light. it sinks over the dark hemisphere. Near the surface, it returns sliding back toward the light. The circulation is broad and steady. It behaves like slow breathing of the whole planet. The day side sends warmth outward above. The night side returns colder air below. A small payoff follows from that loop. If the atmosphere is thick enough, the night side does not become airless. Warm flow keeps gas from freezing onto the ground. A single number gives the rhythm of repetition. The orbit can be about 11 days, a cycle shorter than a fortnight. 11 days repeats often. Winds can push the hottest region away from the point under the star. The hottest area drifts downwind like a warm stain. The infrared glow peaks slightly off-center. A visual anchor forms overhead. Above the day hemisphere, rising air seeds a cap of cloud. The cap resembles a pale dome. Its edge feathers into thin filaments as it spreads. Beneath that dome, the surface can cool. High clouds reflect some incoming light. They also trap outgoing warmth. The day side therefore holds layers: a bright upper haze, a warmer middle layer, a surface layer shaped by winds and terrain. Along the twilight ring, clouds can break into streaks. Streaks align with the gradient and they shear slowly as flows meet. A small payoff settles inside that image. Clouds can move the habitable belt by shifting where heat is kept. The primary analogy takes a natural form. The locked world behaves like a dune field under a wind that never changes direction. One slope stays windward and constantly reshaped. The opposite slope stays leeward and sheltered. Over time, the dune keeps a stable profile. On the planet, the windward side is the day hemisphere. It is shaped by rising motion and outward flow. The leeward side is the night hemisphere. It is shaped by sinking motion and pooled cold. The twilight ring is the crest line. It is where the strongest gradient lives. It is also where narrow jets can form. Jets hug the boundary because pressure changes fastest there. A visual scene slows closer to the ground. Across the ring, darker, bare rock lies beside paler frost. The frost edge is feathered. It advances in fingers into small hollows. It retreats on ridges that catch more slanted light. Above it, air can carry fine crystals. They scatter starlight and create a faint glow on the dark side near the border. Another small payoff arrives. Twilight is not only dim light, it can be a region of gentle energy exchange. Water vapor can condense there. It can fall, then drift as ice grains toward the cold hemisphere. If liquid water exists, it can collect in basins along the belt. It can freeze at the margins and stay liquid in the middle. The limit of observation enters without strain. From far away, the surface cannot be resolved as a map. Only combined light escapes the system. That light mixes day-night and twilight into one changing signal. As the world orbits, different fractions of the warm hemisphere face outward. The infrared brightness rises and falls. The curve can be read as temperature. It can also be read as clouds. A thick cloud dome can hide a hot surface. A thin haze can smooth contrast and imitate warmth. A frosted night side can reflect enough light to confuse the balance. This is a specific limit. Different atmospheres can produce similar phase curves in brightness. Models can narrow options, yet they cannot select a single truth from one curve. A small payoff comes from accepting that limit. Uncertainty points to which measurements matter most, such as changes with wavelength. Scale shifts widen the picture and then soften it again. A single air parcel rises and cools in minutes. A global circulation pattern stabilizes over dozens of orbits. Over thousands of years, tides keep the same face turned inward. Over millions of years, stellar activity can thin upper air and alter chemistry. The locked state persists, yet the climate can drift between stable regimes. The closing scene stays quiet. The day hemisphere glows as a soft disk. The night hemisphere fades into near black. Between them, the twilight ring holds a dim sheen of scattered light. That sheen is thin, yet it carries clues about air and frost and cloud layers. Calmly, the focus shifts from lighting to composition. The next step follows how gases leave narrow fingerprints in light, and how those fingerprints reveal structure in air. A planet can remain unseen in shape and still announce itself in light. In that region, an atmosphere leaves narrow, dim notches that reveal what the air contains. The notches do not look dramatic. They appear as small absences inside a smooth glow. Light behaves as a layered stream. Each layer carries a slightly different color and energy. When that stream passes through gas, some layers are reduced more than others. The reduction forms an absorption line. It is a thin dip at one wavelength. The first quiet unlock settles here. Air can be detected without seeing clouds or continents. Only the light needs to carry a pattern that gas cannot avoid leaving behind. A visual scene forms with slow clarity. A soft ribbon of colour stretches across darkness. The ribbon is not bright like a banner. It is faint like a thin mist lit from behind. Across it, several dark strokes lie like charcoal brushed gently once. Each stroke has a width and a depth. Each stroke has a soft edge rather than a sharp cut. The edges slope down and back up as if the ribbon is gently pressed. Spectroscopy is reading matter by the wavelengths it removes. A piano chord offers an everyday picture. When one note is missing, the chord sounds thinner. When several notes are missing, the chord sounds changed in a specific way. The missing notes point to which strings are damped. In the same calm way, missing light points to which molecules are present. That matters because molecules are the building blocks of air. A second small unlock follows. The strength of a line can hint at the thickness of gas along the path. The path is not always the same. When the planet is seen more from the side, the light skims through a longer slice of atmosphere. The slice is a curved shell. It hugs the planet like a thin skin. Near the limb, the skin becomes a long corridor of air. More corridor means more chances for light to be reduced. The notches can deepen. A physical detail anchors the idea. The limb is a boundary where the planet's disk ends. At that boundary, the atmosphere is a shallow haze that fades outward. The haze is brighter on the day side and dimmer on the night side. It can scatter light in a faint ring. That ring can be thicker near the warm hemisphere. It can thin near the cold hemisphere. A third small unlock settles. Even without a map, the limb can act like a sampler of upper air. The upper layers matter most because they are the first layers light meets. They're also where small particles can float. A high haze can blur lines into broader dips. A clearer sky can leave sharper strokes. The scene slows again to keep the rhythm gentle. The ribbon of colour darkens toward one end. It brightens toward the other. Along its length, one deep notch sits alone. It looks like a river channel cut into sand. Nearby, two shallow notches sit closer together. They look like parallel grooves pressed into soft wax. The spacing between notches becomes a signature. One molecule prefers one spacing, another molecule prefers another. The pattern can be more informative than any single dip. At this distance, the signal remains delicate. A typical notch might reduce the light by about 1 part in 1,000, like one dim tile in a large bright mosaic. That small change is enough to carry meaning. It is also small enough to be confused by other effects. Clouds can mute contrast. Dust can add a smooth veil. Scattering can tilt the ribbon's slope. Another small payoff arrives inside that complexity. A set of lines that rises and falls together across time points to gas, not dust. Gas lines deepen when the path length increases. Dust veils tend to dim broadly without matching the same wavelengths. The story steps into a controlled scale shift. A single molecule interacts with light over a distance smaller than a grain of sand. Yet many molecules together shape a line that spans a wide band of colour. The line is a macroscopic mark. It is the sum of countless microscopic events. The mark can persist over years because chemistry persists. The star's light provides the backlight. The planet's atmosphere provides the filter. The pattern can therefore repeat with each orbit. The repetition is a calm check. If the notches return at the same wavelengths, the air's composition is stable. If the notches drift or fade, the air is changing or obscured. Another visual anchor arrives in slow motion. The planet's disk is not resolved. Only a small change in total light appears as the orbit progresses. During a partial alignment, the planet's limb adds a thin extra layer to the starlight. The extra layer is like a faint ring laid over the star's glow. The ring does not brighten, it slightly dims selected colours. The dimming is subtle, it is also structured. That structure is the clue. The limit of observation arrives softly and specifically. Different atmospheres can create similar line patterns when lines overlap. Overlap happens when lines sit too close to separate cleanly. It also happens when pressure and temperature broaden them into bands. A warm upper layer can spread a line wider. A cooler layer can keep it tighter. If the layers are unknown, the same notch can be explained in more than one way. Clouds add another ambiguity. A high cloud deck can hide deeper layers, and it can make lines appear weaker. A thinner cloud deck can reveal more depth and strengthen the same lines. The measurement therefore depends on models of layering and haze. It depends on how finely neighbouring wavelengths can be distinguished. It depends on how well the star's own spectrum is known. None of these limits are failures. They are boundaries of inference. Another small payoff settles with that boundary. A spectrum is not a single answer. It is a set of constraints that narrows the range of possible airs. Some mixtures become unlikely. Some temperature profiles become less plausible. Some haze thicknesses become more consistent. The calm work is to gather enough constraints that the remaining picture is stable. The section returns to imagery to keep the breathing easy. The ribbon of colour now looks like a shoreline at night. Dark inlets cut inward where lines deepen. Pale sandbars lie where the light stays smooth. The inlets widen and narrow with changing geometry. They never jump. They shift gradually like tides changing depth along a coast. A final scale shift widens the frame. The planet's orbit repeats in days. The atmosphere can persist for millions of years if it is replenished or protected. The star's light takes years to cross the gap between stars in the system, yet a single spectrum can carry the imprint of molecules that are smaller than dust grains. The next section turns from composition to motion within air. It follows how heat gradients drive circulation, and how a locked world redistributes warmth without changing its face. A locked world can look divided, yet its air keeps trying to blur the line. In that region, steady winds move heat from the bright hemisphere toward the dark, and the climate becomes a slow conveyor. The day side receives constant energy and builds a dome of warmer air. Warmer air expands. It becomes lighter and rises. Above the brightest point, a broad column lifts upward like a slow fountain that never stops. The column spreads at higher altitude. It thins into a sheet that glides away from the light. The first quiet unlock appears. A permanent day does not guarantee a permanent furnace. Rising air can cool the surface by carrying heat upward and outward. The surface under the lift can become less extreme than expected. A visual scene settles into focus. A pale cloud canopy forms a smooth oval around the brightest region. Its edge is scalloped. Thin filaments peel away and trail toward the twilight belt. Beneath the canopy, the infrared glow looks like a teardrop. The brightest patch sits slightly downwind. The shift is gentle. It suggests that wind, not sunlight alone, sets the hottest place. Pressure differences drive that wind. Pressure is the weight of air above a point. On the warm side, air columns are taller. On the cold side, columns shrink. The difference builds a slope in pressure like a low hill in an invisible landscape. Air slides downhill along that slope. It does so in wide arcs because the planet still rotates. Rotation bends moving air sideways. The bending is not a choice. It is a consequence of motion over a turning surface. The second quiet unlock settles. Even on a world with the same face toward its star rotation, still sculpts wind into bands and jets. The boundary between day and night becomes a preferred track. Along that boundary, temperature changes fastest. Faster change means sharper pressure gradients. Sharper gradients can produce narrower, stronger winds. A ribbon-like jet can wrap the planet near the twilight ring. It can be strongest at higher altitude. Below it, slower return flow creeps back toward the day side near the ground. Another visual anchor arrives with patient detail. The twilight ring is a long band of dusky light. Along it, cloud streaks align like brushed satin. Some streaks brighten where air rises along the boundary. Some streaks thin where air sinks. On the night side, the sky clears into a deep, cold dome. Near the surface, frost spreads into lobes. The lobes have feathered edges and smooth interiors as if cold pours like liquid into low basins. At higher altitude, a faint haze can drift carried from the day side like smoke from a distant unseen source. A small payoff settles in the contrast. The coldest place is not always the farthest from light. It can be where sinking air concentrates cold and dryness. Sinking air warms slightly as it compresses, yet it also dries. Dry air radiates heat away efficiently at night. The night hemisphere can therefore become an efficient radiator. It can act like a dark mirror for thermal energy. That mirror is not shiny. It is simply open and clear. The consequence is a climate that tries to balance itself. Heat rises on the day side. Heat leaves to space on the night side. Between them, winds stitch the two halves together. A single number gives the motion a tangible pace. The jet near the boundary can reach about 100 kilometers per hour like a strong gale that can lift fine sand into a low veil. At that speed, air can circle the planet in a few days. That circulation time can be comparable to the orbital period on a close world. The third small unlock appears. When transport time is short, temperature contrast shrinks. The day side remains brighter and warmer, yet the night side avoids becoming utterly frozen. The planet becomes less like a split stone and more like a gradient sphere. The gradient has structure. It has layers. Near the surface, friction slows flow. Above, air moves more freely. A temperature inversion can form where warmer air sits over cooler air. The inversion can trap clouds below. It can also trap hazes above. The dayside canopy can become a steady lid. The lid reflects incoming light. It also traps outgoing heat. The two effects pull in opposite directions. Reflection cools the surface. Trapping warms the lower air. The balance depends on particle size and thickness. Fine particles scatter more. Larger droplets absorb more. The details matter because they alter the infrared glow that escapes. Another calm payoff settles. A bright cloud deck can hide a hot surface. A clear sky can reveal a cooler surface that radiates efficiently. The same total brightness can arise from different vertical structures. The limit of observation sits exactly there. From far away, the planet is not a disk with weather maps. It is a point whose light changes with phase. The rise and fall of infrared brightness across an orbit combines day-night and boundary into one curve. Different wind patterns can produce similar curves. A strong jet that shifts the hottest region can mimic a thicker cloud canopy that shifts emission altitude. A hazy atmosphere can blur contrast and imitate faster heat transport. These are not vague uncertainties. They are specific degeneracies where two different causes lead to the same distant signal. The limits come from resolution, and from the hidden vertical layering that a single band of light cannot fully separate. Another visual scene returns to ground the mind. Along the twilight belt, the surface shows alternating patches. Dark rock absorbs slanted light and warms. Pale frost reflects and stays cooler. The boundary between them is a thin, wavering line. It advances and retreats with wind, not with sunrise. Small eddies can curl along ridges. They lift dust or ice grains into faint curtains that glow softly when lit at an angle. The curtains have smooth gradients thickest near the ground and fading upward. A small payoff settles in the shape of those curtains. They mark where air is moving upward from the boundary. Upward motion can carry vapour into colder layers. There it can condense into high haze. That haze can thicken the canopy on the day side and extend it into the twilight band. The canopy then feeds back on temperature. The system becomes a loop of cause and response. Heat drives wind. Wind drives clouds. Clouds reshape heat. The loop can stabilize into a steady pattern. It can also shift between modes over long times. The scale drift becomes gentle and wide. A single gust forms in minutes. A jet band persists for months. Over thousands of orbits, the average pattern can remain recognizable. Over millions of years, changes in stellar activity can thin upper air, and the circulation can adjust. The locked state persists, yet the atmosphere can evolve from thick to thin, from clear to hazy, without changing the basic geometry of light and shadow. The section settles into a quiet, closing image. The dayside teardrop of warmth remains offset by wind. The twilight ring remains a thin sash of cloud streaks. The night side remains a smooth bowl of darkness with frost pooling in lowlands. Within that calm motion, the next step approaches the invisible shield around a planet. In that region, charged particles from the star meet magnetic boundaries, and the shape of protection becomes part of the climate. A planet can be wrapped in an invisible shape that changes how the star touches it. In that region, a magnetic field can deflect charged particles and slow the loss of air. The flow from the star is not empty light. It includes a wind of charged particles that streams outward and carries its own pressure. When that wind meets a world with a magnetic field, it cannot pass straight through. It bends, it slides around. The bending creates a boundary. The boundary is not a wall of matter. It is a place where forces balance. Magnetosphere means the region controlled by a magnetic field. It is defined in simple terms. It is the space where the planet's field dominates the motion of charged particles. Like a smooth stone in a current, the flow splits and reunites downstream. The important part is not drama. The important part is that the densest stream is redirected away from the upper air. A small unlock settles early. Protection does not need thickness. It needs shape. The shape appears first as a bow shock. It is a curved front ahead of the planet where the wind slows and heats. The curve is broad. Its edge is soft. It resembles a slow wave crest frozen in place, always facing the oncoming flow. Behind it sits the magnetopause, another curved boundary where the flow is excluded more strongly. Between these two layers, particles swirl and slide, trapped in a sheath of compressed plasma. The physical detail is clear. Two nested arcs form a layered shell. Each arc has a gradient, denser flow outside, thinner flow inside. A visual scene forms with calm precision. The planet itself remains a dark disk. Ahead of it, an invisible crescent of pressure stands off from the atmosphere. Behind it, the shield stretches into a long tail. The tail narrows. It becomes a tapered ribbon that trails away in darkness like smoke, pulled into a steady draft yet without any smoke. In that tail field, lines guide charged particles in long loops. Those loops can close back to the planet on the night side. Another small unlock appears. A shield does not only block, it also channels. Some particles are guided toward the poles where field lines converge. Near those polar regions, collisions with upper air can produce faint glows. The glows form oval arcs that hug the high atmosphere. They are thin bands. They brighten and dim as the wind pressure changes. The arcs are not steady flames. They are shifting curtains of light that ripple along the boundary between space and air. The curtains reveal that the upper atmosphere is not a solid lid. It is a layered gradient. Density drops with height. Temperature can rise again in the high layers. Charged particles deposit energy into that thin region, and the region responds by shining softly in specific colours of emission. The analogy shifts to something that stays natural and unique. The magnetosphere behaves like a reed bed in a river. The main current is diverted around the stems. Some water still threads through, but it slows and spirals. The reeds do not stop the river. They reshape its path and reduce its direct impact on the bank. In the same way, the field reshapes the incoming stream and protects the densest parts of the atmosphere from direct scouring. The protection is not perfect, it is dynamic. When the stellar wind strengthens, the bow shock moves inward. When it weakens, the boundary relaxes outward. A single number anchors the scale. The standoff distance can be about 10 planet radii, like a canopy that reaches 10 trunk widths beyond a tree's centre. That distance is not a measurement of comfort. It is a measure of breathing room. More room means more space for particles to be diverted before they reach dense air. Another small unlock settles. The size of the cavity matters more than the exact strength of the wind at any one moment. A larger cavity reduces the average energy that reaches the upper atmosphere over time. Without a strong field, the wind can press directly on ionized upper air. It can strip particles away. It can carry them off along magnetic lines that are not anchored to the planet. This process is atmospheric escape. It is air leaving to space over long time. Escape does not happen as a sudden gust. It happens as a slow leak molecule by molecule. The leak is guided by energy deposited high above where gravity is easier to overcome. The scene tightens down to the microscopic scale. A single charged particle spirals around a field line in a tight helix. The helix is tiny. It is far smaller than a grain of dust. That spiral motion is what makes the field effective. It forces the particle to follow curved paths rather than straight plunges. Multiply that by countless particles and the boundary becomes a living surface. It shimmers in density. It flexes under pressure. Then the scale drifts outward again. The magnetotail can extend far beyond the planet, longer than the distance across the planet by many orders of magnitude. It becomes a long wake in the star's wind. In that wake, reconnection can occur. Reconnection is when magnetic lines break and rejoin. It releases stored energy. It can send bursts of particles down toward the poles. It can also fling particles outward down the tail. Another small payoff arrives. A planet can lose air even with a field if reconnection opens pathways often enough. Protection is not a binary switch. It is a balance between shielding and openings. The balance depends on how the wind presses. It also depends on how fast the planet rotates and how its internal field is shaped. A tilted field creates a wobbling cavity. A more aligned field creates a steadier one. The physical details remain vivid. The bow shock is a smooth arc. The magnetopause is a second arc closer in. The tail is a tapering tube. Inside the tube, two lobes can form, separated by a thin central sheet where current concentrates. The sheet is a plane of change. Above it, field lines point one way. Below it, they point the opposite way. Where they meet, the system is sensitive. A small unlock settles in that geometry. The places of greatest change are also the places where energy is converted most efficiently. Those places can control escape rates more than the average conditions elsewhere. The limit of observation arrives softly and clearly. A magnetic field cannot be seen directly as a picture at this distance. Its presence must be inferred from secondary effects. A signal would appear as periodic radio emission tied to rotation, yet that signal can be weak or masked. A signal would also appear as certain ultraviolet glows, yet those glows can be produced by other heating processes. An object would show slower atmospheric loss if a cavity exists, yet composition and gravity can mimic that stability. These are specific ambiguities. Different mechanisms can create similar signs. The inference therefore depends on consistency across time and across wavelength. It depends on whether emissions respond to changes in the star's wind in the expected way. Another small payoff settles inside the limitation. Uncertainty does not erase meaning. It highlights which patterns are robust, such as a recurring polar oval or a stable modulation that matches rotation. It also highlights which patterns are fragile, such as a single brightening that could be a transient flare in the star. The section returns to a slow visual anchor to steady the tone. The dark planet moves through a stream that is never truly still. Ahead of it, an invisible arc holds its curvature. Along the arc particle, density rises smoothly, then falls. The arc casts no shadow, yet it defines a shape in the darkness. Behind the planet, the long tail narrows into a ribbon that fades by gradients, denser near the centre and thinner at the edges. Within that ribbon, faint polar curtains appear and soften, as if the upper air is gently combed by distant hands that are not hands at all, only feels and flows. The scale shifts one last time. Minutes of wind variation create small compressions. Years of orbit create repeated cycles of stress. Millions of years decide whether an atmosphere remains thick, thins to a haze, or becomes a trace. In that long view, the shield is one of the quiet architects of habitability. It is also one of the quiet sources of light through faint emissions at the poles and along boundaries. The next section moves from charged particles to solid grains. In that same system, dust can glow and drift. It can reveal collisions and rings that persist as slow, delicate structures. A faint ring of dust can be the calmest proof that a system is still active. In that region, glowing grains imply that collisions keep making new material faster than it can disappear. The space around the bright pair is not a clean vacuum. It carries a thin population of solids. Some are large bodies that stay dark and silent. Some are tiny grains that warm quickly and shine. In infrared light, those grains can outshine their own mass. A small payoff settles at once. Dust is temporary. If dust is seen, something is feeding it. The physical scene is quiet and wide. A narrow belt of warmth curves around the stars. The belt is not uniform. One side looks thicker and brighter. The other side fades into a soft gradient. The inner edge is slightly sharper, like a boundary traced with steady pressure. The outer edge feathers away as if the material is gradually thinned and dispersed. Light behaves as heat in this view. Each grain absorbs starlight. It re-radiates that energy at longer wavelengths. The belt becomes visible as a temperature map. Warmer grains mark closer orbits. Cooler grains mark farther lanes. The belt's brightness therefore hints at distance and density without showing any single particle. Another small payoff follows. Temperature can locate dust even when the grains are too small to resolve. The grains themselves are small. A typical grain can be about 1 micrometer across, comparable to a pollen grain. That size matters because small solids interact strongly with light. They're easy to warm. They're also easy to push. Radiation pressure is light pushing on matter. It is defined in simple terms. It is the gentle force from photons striking a surface. Like a breeze that lifts dry seeds, light can nudge the smallest grains outward. Some grains are pushed onto wider orbits. Some are pushed out of the system entirely. The belt cannot survive on old dust alone. It must be replenished. The checkpoint moves inward to the source. Large bodies collide. A collision shatters rock and ice into fragments. Those fragments collide again and make finer grains. Collisional cascade is repeated breakups that make ever smaller debris. 2 sentences make it tangible. It is like brittle stones in a stream that knock and chip with every bend. Over time the stream fills with sand even if no sand was carried in. The reason it matters is quiet and direct. A cascade creates the small grains that glow and respond to light. A visual anchor arrives with slow detail. Near the belt a loose cloud of grains drifts. It is not a dense fog. It is more like a faint veil. Within it, a slightly brighter knot appears. The knot is not a fixed object. It is a region where many orbits overlap. The knot stretches into a short arc over time. The arc is brighter at its centre and dimmer at its ends. Its edges are soft. The arc hints at a recent collision that has not yet mixed fully into the belt. Another small payoff settles. A single collision can leave a temporary signature that fades as the system stirs it. The stirring is steady. Orbits shear material. Inner lanes move faster than outer lanes. A compact cloud becomes a curved smear. The smear becomes a broader ribbon. The ribbon becomes part of the belt. This is motion without urgency. It is geometry unfolding. The belt structure therefore contains a timeline. Sharp features suggest youth. Smooth features suggest age and mixing. The scale shifts down again to the grain level. A grain tumbles. It has facets. It has pores. It may carry a thin coating of ice. Those details change how it absorbs and re-radiates heat. A darker grain warms more. A brighter grain stays cooler. The grain's temperature sets the wavelength of its glow. Many grains together form a spectrum. That spectrum can reveal size distributions because small grains radiate differently than large fragments. Another small payoff follows. The colour of the infrared glow can hint at whether the belt is dominated by fine dust or by larger crumbs. The story then widens to the balance of forces. Gravity pulls inward. Light pressure nudges outward on small grains. A slower effect drags grains inward over long time. It comes from the fact that re-emitted light carries momentum. A grain slowly loses orbital energy as it re-radiates. It spirals inward. This drift is gentle. It is slow compared to an orbit. It matters because it empties the belt from the inside if nothing refills it. The belt that remains bright must therefore be constantly topped up. Another visual anchor steadies the mind. The belt looks like a soft bracelet of warmth around the stars. At one location, the bracelet is slightly thicker. It resembles a place where powder gathers in the crease of a leaf. The crease is not carved by a tool. It is created by shape and flow. In the same way, the thickened region can be created by orbital crowding. Crowding can happen near resonances where paths align. It can also happen where collisions are more frequent. Another small payoff settles here. Thickness does not always mean more material overall. It can mean the same material spends more time there. This distinction becomes important when interpreting faint light. The limit of observation arrives softly and clearly. A distant view cannot count grains. It cannot directly separate a recent collision cloud from a stable belt if both are faint. It can only measure combined glow in its spectrum. Different combinations can produce similar brightness. A belt with many cool grains can mimic a belt with fewer warm grains if their total emission matches. Grain composition also confuses the picture. Icy grains scatter and emit differently than rocky grains. A haze of very small particles can make the spectrum smoother and hide the signature of larger pieces. These limits are not vague. They are degeneracies of inference where multiple causes fit the same light. Another small payoff settles in the response to that limit. Time can break the tie. If the belt's brightness changes slowly, it suggests ongoing collisions. If a knot stretches and fades, it suggests one recent event. If the spectrum shifts toward warmer emission, it suggests inward drift or smaller grains. If it shifts cooler, it suggests grain loss or a quieter cascade. The rhythm stays calm because the clues are gradual. The section returns to a broad-scale shift. A collision happens in an instant. The resulting dust can remain detectable for many orbits. Over millions of years, the belt's presence implies that larger bodies still exist and still collide. Those unseen bodies form a reservoir. They are the slow engine behind the visible veil. In that long view, dust is not clutter. It is the system's memory written in thermal glow. The closing image settles gently. The warm belt arcs around the stars. Its inner edge stays slightly sharper. Its outer edge fades like mist thinning into clear air. A few subtle bright patches sit along it, and then soften as orbital shear spreads them into the band. The next section follows how gravity can etch that band into lanes and gaps, and how repeated timing leaves clean structure inside a quiet ring. A dust ring can look smooth, yet gravity writes fine grooves into it with time. In that region, repeated tugs organize debris into lanes and gaps without any sudden violence. The material begins as a broad belt. Collisions feed it with grains. Drift and pressure spread it. Then rhythm appears. The rhythm comes from orbits that repeat at commensurate times. Resonance is repeated gravitational nudges that add up. It is defined simply. It is a pattern of timing that reinforces itself. Like footsteps on a bridge that arrive at the same beat, small forces can build noticeable effects. The first calm unlock settles. Structure in a ring does not require a sculptor. Timing alone can sculpt. The physical scene forms as a record of these beats. A warm ring arcs around the bright stars. Within it, a thin, dark lane runs like a seam. The lane is not empty. It is merely depleted. Its edges are sharper than the belt's outer fade. The lane's inner rim looks slightly brighter. Grains pile there. The outer rim looks softer. Grains diffuse away. The lane is a boundary between two orbital neighborhoods. On one side, grains linger longer. On the other, grains are stirred and scattered. A visual anchor arrives with slow tactile clarity. The ring resembles a piece of wood seen in oblique light. Fine growth rings appear as alternating bands. Some bands are darker and narrow, some are brighter and wider. A knot in the wood becomes an arc in the dust. The analogy remains quiet because it is about layering, not drama. The important point is that a ring can hold memory. Each band encodes where material spends time. The checkpoint moves to how bands form. In a binary system, the central pull is not from one fixed point. It changes as the two stars move. Their combined gravity creates a time-varying pattern. A small object feels a tug that depends on where the stars are in their orbit. When the tug repeats at a consistent phase, the object's own orbit shifts. Sometimes it is pushed slightly inward, sometimes outward. Sometimes its orbit becomes more elongated. Those changes are small per cycle. Over thousands of cycles, they can become visible in the ring's architecture. Another small payoff settles. A gap can be an archive of small repeated changes. It can indicate that certain orbits are systematically cleared. It can also indicate that orbits become unstable and fling grains into other lanes. The ring becomes a map of what is allowed and what is discouraged by the central dance. Physical detail deepens the image. The brighter bands are not uniform circles. They can be slightly offset. One side can be denser. The density enhancement appears as an arc. The arc is thicker near a particular azimuth. It thins as it wraps around. The arc is a place where orbits crowd like traffic slowing near a bend. The crowding does not mean a pile-up. It means that many paths overlap there for longer. The overlap raises brightness. It also raises collision rates, which can make even finer grains and increase glow. Another small payoff settles. brightness can indicate time spent as much as mass present. A new number anchors the scale of repetition. A grain near the ring might complete an orbit in about 1 year, like a seasonal cycle on a calendar. In a year, the central stars move only a small fraction of their long dance. In a few decades, the binary geometry shifts substantially. Over those decades, resonant locations drift. The ring responds slowly. New lanes can deepen. Old lanes can soften. The ring is therefore not a frozen sculpture. It is a living pattern, yet it moves with patient speed. The scale then shifts down to a single grain again. A grain drifts inward by tiny steps as it radiates heat. Its orbit shrinks slightly. As it crosses a resonance, the repeated tug can change its path abruptly and angle, not by force but by accumulation. It can pump the eccentricity. The orbit becomes more oval. The grain then spends more time far from the stars. It cools there. It shines less. It also crosses the ring at different angles and collides more often. The collisions can destroy it. That is how a lane can clear, not by sweeping but by making survival harder. Another small payoff arrives. A resonance can be a filter that selects which grain sizes persist. Small grains are pushed by light more. Large grains resist. Medium grains may be most vulnerable. The ring's colour and brightness can therefore encode size distribution. A darker lane might be depleted of one size more than another. The lane can also shift with time as the population evolves. Another visual anchor appears to keep the rhythm slow. Imagine a broad sheet of mist lit from behind. A comb passes through it once. The teeth do not remove all mist. They leave faint channels where flow changes. The channels persist because the same motions repeat. In the ring, gravity is the comb. Resonances are the teeth. The channels are lanes and gaps. The image stays quiet because it is about gentle organization. The section approaches the limit of observation with care. From far away, the ring cannot be seen as a crisp image unless contrast is high. Often it is inferred from a glow profile. The profile is brightness as a function of distance from the stars. A dip in the profile can indicate a gap. It can also indicate cooler grains rather than fewer grains. Composition can alter emissivity and shift where the ring appears brightest. A warp in the ring can create apparent dips when the line of sight changes. In a binary system, the star positions change the illumination pattern as well. These are specific limits. A brightness dip is not uniquely a density gap. It could be a temperature change, a tilt, or a change in grain size. The inference relies on multi-wavelength consistency and on how the profile changes with time. Another small payoff settles. If a dip appears at the same location across wavelengths and across seasons, it is more likely a true gap. If it shifts with wavelength, it may be temperature or composition. If it shifts with time in step with the binary geometry, it may be illumination rather than structure. Time again becomes a gentle tool. The ring is read through its stability and its slow evolution. The scale widens into a longer story. The ring may persist for millions of years if collisions continue among unseen bodies. Over that time, resonances can shepherd material into belts. They can also drive material into the stars or out of the system. The ring becomes both a reservoir and a sink. Its lanes mark the pathways of long-term transport. Its arcs mark the places where orbits crowd and collide. The closing image settles softly. The glowing belt curves around the bright pair. Inside it, a thin seam darkens a narrow radius. Along one sector, a brighter arc thickens like a quiet swell on a calm sea. Nothing flashes. The pattern simply holds and drifts. The next section turns from passive structure to deliberate suppression of glare. It follows how darkness can be used as a geometry, allowing faint companions to separate from the bright halo without ever resolving their surfaces. Sometimes the brightest light reveals more when it is gently reduced. In that region, an occultation briefly lowers glare and lets faint structure separate from the halo. The scene begins as a steady disk of starlight. Around it sits a soft ring of spill, fading by gradients into darkness. The ring is not dust, it is the wave spread of light. In ordinary view, that spread buries anything faint nearby. Then a darker silhouette drifts across the star's face. The silhouette is small in angular size, yet its effect is large in contrast. Occultation means one body passes in front of another. In plain terms, it's a moving shade. Like a thin cloud crossing the moon, it lowers brightness without changing the sky. That matters because the lowered brightness also lowers the halo's slope. The first quiet unlock settles. Darkness can act like separation even when distance stays the same. A visual anchor forms in slow motion. The star's disk is partially covered by a crisp crescent of shadow. The covered edge is clean. The uncovered edge remains bright. Around the disk, the halo contracts in intensity. It does not vanish. It becomes a shallower glow. In that shallower glow, a faint point can hold its shape longer. A faint arc of dust can become visible as a soft line instead of a smear. The masked moment is brief, yet the change in balance is immediate. Contrast improves because the brightest core is reduced. The nearby field stops being washed out by a steep gradient. The second calm unlock appears. A faint companion does not need to brighten. The background needs to dim. The mechanism is simple, yet its outcomes are subtle. When the silhouette crosses, the light drop is not uniform in time. It begins with a smooth decline. It reaches a minimum. It rises again. The shape of that dip carries geometry. A sharp ingress suggests a hard edge. A rounded ingress suggests a blurred boundary or a grazing pass. A dust veil would produce a softer slope than a solid limb. The dip also depends on where the silhouette crosses the disk. A central pass blocks more light. A high-latitude pass blocks less. The halo responds in parallel. As the core dims, the halo's brightest rings become less dominant. The field becomes more forgiving. Another visual anchor arrives slower and wider. Beyond the star, the nearby space shows faint material as a pale band. The band has a slightly darker notch. The notch sits at one radius. Its edges are not equally sharp. One side looks stepped like a gentle terrace. The other side fades like mist. During the dimmed interval, the notch becomes easier to distinguish from the general glow. It is not newly created. It is newly separable. A small payoff settles. An occultation can function like a brief lowering of the curtain, revealing a stage that was already there. Light behaves as waves here, and waves create rings. Diffraction is wave bending that spreads light into rings. It is defined simply. It is light spreading around edges into a patterned halo. Like ripples meeting a pier, the wavefront does not stop. It bends and interferes. That matters because a bright star is never a perfect point. It is surrounded by structured spill. When a silhouette covers part of the star, the spill pattern can change. It can become asymmetric. One side can dim more than the other. That asymmetry can briefly open a cleaner region. In that region, a faint point can stand out. Another payoff settles. A changing halo pattern can be a clue to the mask itself, not only to the companion. The mask could be a planet. It could be a ringed body. It could be a compact dust sheet. Each leaves a different imprint on timing and wavelength. A ringed body produces a dip with shoulders. A dust sheet produces a shallower dip that varies with colour. A bare, solid limb produces a cleaner edge. The story remains calm because the changes are small. A typical dip might be about 1 part in 10,000, like one missing grain in a heap of sand. Such a small change is still measurable in principle. It still demands patience. It also demands repeated events. A single dip can be an accident of noise. Repetition makes it a pattern. Another visual anchor steadies the view. The star's disk shines like a smooth coin of light. The silhouette crosses it as a darker bead. Around the bead, the starlight continues to leak. Yet the bead's edge remains crisp against the bright surface. As it moves, the edge traces a chord across the disk. Behind it, the brightness recovers as if a thin veil is lifted. The nearby faint point remains in place relative to the star, then resumes being drowned as the core returns. The small payoff inside this image is direct. Timing can separate fixed background from moving foreground. If the faint point stays steady while the star dims, it becomes more likely to be real. If it flickers in step with the halo changes, it may be an artifact of spill. Scale shifts make the logic feel gentle and grounded. The silhouette edge is a boundary measured in thousands of kilometers. The crossing time can be hours. The orbit that sets up the alignment can take days or years. Over long times, alignments repeat only if the geometry stays coherent. That coherence is fragile in a multi-star system. The bright pair shifts its own orientation. Dust belts precess. The path of a planet can tilt. The chance of a perfect crossing can be low. This becomes the limit of observation. Occultations rely on alignment, and alignment is not guaranteed. A faint world can exist and never cross the star from this vantage. A ring can exist and never produce a clear shoulder. A dust sheet can exist and mimic a clean dip if its density gradient is steep. There is another limit as well. Stellar surfaces are not perfectly uniform. Dark patches and bright regions can change brightness in ways that resemble shallow dips. A star can vary gently and confuse an event that is already tiny. These are specific constraints. The method depends on distinguishing a geometric dip from intrinsic variability. It depends on resolving shape in time. It depends on separating wavelength-dependent dimming from wavelength-independent dimming. It depends on models of the star's own limb darkening, which can blur the edges of any event. Another small payoff settles in response to that limit. Even when an occultation is ambiguous, it still narrows what is possible. A dust sheet that dims more strongly in one color becomes more plausible. A solid limb that keeps the dip similar across colors becomes more plausible. A ringed body that adds shoulders becomes more plausible. Each piece does not end the search. It refines the space of explanations. The calm power comes from stacking small constraints. The final visual anchor arrives as a slow return to the wider field. The bright star resumes full intensity. Its halo expands into a familiar gradient. The faint arc of dust recedes into the glow. The faint point near the star becomes harder again. Yet the memory of the masked interval remains as a short segment of cleaner separation. It suggests that the system can be read through moments, not only through averages. The next section turns from these brief clean moments to the longer map of where orbits can survive. It follows the narrow harbours of stability that exist between strong tugs and slow, resonant clearing. A world can exist in a binary system only if its path learns a quiet compromise. In that region, stable zones are narrow harbours where repeated tugs fail to accumulate. Around the bright pair, gravity is not a single steady pull. It is a pattern that shifts as the stars circle their shared centre. Each moment has a slightly different balance. A small body feels those changes as gentle nudges. The first calm unlock settles early. A stable orbit is not perfectly undisturbed. It is simply self-correcting enough to remain bounded for a long time. A visual scene forms in slow darkness. Two bright disks sit close. Around them a faint oval glow marks a dust belt. Inside that belt a thinner lane appears where the glow is reduced. The lane is shaped like a soft eye. Its edges fade by gradients, not by sharp cuts. The eye is a region where grains do not linger. It is a region where paths are repeatedly disturbed. The belt outside the eye looks smoother. It holds a quieter rhythm. The checkpoint moves from what is seen to what it implies. Orbits near one star can remain stable if they are tight enough. The companion star then becomes a distant influence. Its tug varies with phase, yet it stays a smaller fraction of the main pull. Orbits far from both stars can also remain stable. Far away, the pair acts more like a single mass. Between those two regimes lies a transition zone. In that zone, the secondary tug arrives at just the wrong times. A small payoff appears. The dangerous region is not defined by distance alone. It is defined by timing. Timing means how often the orbit lines up with the binary phase. If the alignment repeats, the same push happens again and again. If the alignment drifts, pushes arrive out of step and cancel. Perturbation is a small repeated change in an orbit. It is defined simply. It is a nudge that alters the path a little each time. Like a leaf carried near a slowly pulsing whirlpool, the path can either be trapped in a safe loop or drawn into a wandering spiral. The analogy stays gentle because the forces are gentle. The outcome is determined by repetition. Another visual anchor arrives to keep the rhythm slow. Imagine a thin ring of dust seen edge on. Its brightness is not uniform. One arc appears thicker, another arc is faint. A narrow notch cuts the ring at one radius. The notch is not empty. It is merely thinner. The ring looks like layered silk wrapped around twin lights. The layers are slightly offset. Some layers overlap into brighter bands, some separate into darker seams. A small payoff settles. The seams are where orbits avoid spending time. The bands are where orbits crowd. This crowding can happen even without any planet. It can be caused by the binary forcing, in that forcing certain longitudes become preferred. Grains can linger in arcs. Other longitudes become unfriendly and clear. This creates the illusion of structure with no single sculptor. The story then steps closer to the physics of long-term drift. A stable orbit must keep its shape from growing too oval. Too much oval shape causes close passes to one star. Close passes increase the next perturbation. The perturbations then grow faster. This is a gentle form of runaway. The second calm unlock appears. Instability often begins as a slow increase in eccentricity, not as a sudden ejection. The increase can take many cycles. During those cycles, a body can still look well behaved. Only later does it cross a threshold where close approaches become common. That threshold is not a single line. It is a fuzzy border where outcomes depend on initial conditions. A single number anchors the scale without sharpening it too much. A stable circumbinary orbit might need to sit at least about 3 times farther out than the separation of the two stars, like a wide moat around a small island pair. This ratio is not universal. It is a useful order of magnitude guide. It hints that the closest safe paths around both stars are not truly close. They begin only after a buffer zone. Another payoff settles. The closest stable circumbinary worlds are forced to keep distance even if warmth would be better nearer in. That distance changes what climates are possible. The warmth drops with distance. The orbital period lengthens. Seasons of illumination can become slower. At the same time, orbits very close to one star can be stable only if they are tight. Tight orbits create stronger tides. They can lock rotation. They can reshape atmospheres. The stability map therefore connects directly to habitability conditions without invoking any living observer. A visual scene returns in slow layers. Near one star, a tight family of paths forms nested loops like ripples around a pebble, each loop slightly shifted by the second star's tug. Farther out, the loops break into rosettes. The rosettes precess slowly. Their petals are not drawn. They are traced by repeated passes of the same body. In the intermediate zone, the rosettes become irregular. Petals thicken. The track begins to smear. This smear is the signature of chaos. Chaos here does not mean random motion, it means sensitive dependence on the exact starting state. Two nearly identical starts can diverge over time. The limit of intuition arrives with that sensitivity. It is hard to predict long-term stability from one short segment of motion. A path can look smooth for years and still be doomed over longer spans. The limit of observation is equally concrete. Only partial information about an orbit can be inferred at this distance. The inclination and eccentricity can remain uncertain. Small uncertainties matter most near the stability border. Models can map likely safe zones, yet the edge remains probabilistic. Another small payoff settles. A probabilistic edge still guides search. It tells where long-lived worlds are less likely. It also tells where dust gaps should appear if clearing is efficient. If a belt shows a persistent eye-shaped thinning, it hints at a sustained unstable region. If the belt shows arcs that remain fixed in phase, it hints at stable resonant trapping. Time becomes the quiet filter again. Changes that repeat with the binary period indicate forcing. Changes that drift steadily indicate precession. Changes that fade indicate transient collisions. Scale shifts widen the view and then calm it. A single grain can be perturbed in seconds during a close pass of the star's alignment. The orbit shape can evolve over thousands of cycles. The architecture of belts and gaps can settle over millions of years. Over those spans, the system selects which paths endure. It does not do so abruptly. It does so through cumulative nudges and gradual clearing. The section closes on a calm image. The twin stars continue their long dance. Around them, the dust belt holds a smooth glow. Within it, a soft eye of reduced brightness remains marking where paths are seldom safe. Beyond that eye, a wider band looks steady and patient. The next section moves from where worlds can survive to how a world can be sensed at its edge. It follows the thin limb of an atmosphere and the layered scattering that shapes its faint ring of light. A planet's edge can glow more clearly than its face. At this distance, a thin limb of air reshapes starlight into a faint ring that reveals layering. The view begins with a dark disk that holds no detail. Around that disk, a narrow crescent appears where light grazes the atmosphere. The crescent is not uniform. It brightens near the tangent point and fades outward in a soft gradient. The edge looks slightly thicker on the warmer side. It looks thinner on the colder side. This early pattern offers a quiet unlock. The atmosphere announces its thickness through geometry before chemistry is even considered. Light behaves as a path that can be bent and scattered. Near the limb, the path is long. It threads through a shallow shell rather than plunging straight down. Scale height means the altitude where pressure drops by a factor of about 3. The idea is simple in practice. A taller scale height makes the limb look puffier. A shorter scale height makes it look tighter and sharper. The why is immediate. The limb's apparent thickness sets how much starlight is filtered. A visual anchor settles in slow detail. The crescent resembles a thin opal rim. It has a bright inner edge and a softer outer veil. Tiny irregularities appear along it like faint scallops in the glow. Those scallops are not mountains in view. They are changes in haze density along the limb. The air is not perfectly clear. It holds suspended particles. They can be droplets, ice, or dry grains. Scattering is light, redirected by particles. It is defined as simply. It is light taking a new direction after meeting small matter. Like morning fog around a ridge, scattering turns sharp light into a gentle glow. Two familiar effects follow. Shorter wavelengths scatter more easily. Longer wavelengths pass more cleanly. This matters because colour becomes a probe of haze. A second quiet unlock appears. A bluish limb can imply fine particles aloft. A redder limb can imply larger particles or clearer air. The limb is also shaped by refraction. Refraction is bending of light in a gradient of density. It is defined simply. It is a curved path caused by changing air thickness with height. Refraction can hide deeper layers. When the bend is strong, the light path never reaches the surface before it turns away. The visible atmosphere then becomes only the upper shell. This limitation is not abstract. It means that a dense lower atmosphere can exist and still remain unseen in transmission. Another visual anchor arrives. The crescent thickens into two layers. A brighter inner band hugs the disk. A dimmer outer band drifts beyond it. Between them lies a subtle trough of lower brightness. The trough suggests a gap between haze decks. One deck sits high and thin, another sits lower and denser. The layers resemble stacked fog banks along a cold shoreline. Each bank has a crisp upper boundary and a feathered lower fade. Another small unlock settles. Vertical layering can be inferred from how the brightness changes with wavelength. A high haze often flattens spectral features. A clearer upper layer allows sharper absorption strokes to remain visible. The limb therefore connects structure to chemistry. A path through clear upper air can show deep notches. A path through hazy upper air can show only a smooth slope. The concept stays gentle. The atmosphere is a filter with variable translucence. A single number anchors the physical scale without forcing precision. The bright part of the limb can correspond to about 10 kilometers of effective altitude, like the height of several tall mountain ranges stacked. 10 kilometers is small compared to a planet's radius, yet it is large compared to the size of any particle. This scale shift brings a calm payoff. A vanishingly thin fraction of the planet can dominate the signal. The limb is a boundary phenomenon. It carries disproportionate information because it multiplies path length. The story moves through another checkpoint. Heat and circulation change the limb around the terminator. On a locked world, the terminator is a permanent twilight belt. Warm air rises on the day side and flows outward aloft. Cold air sinks on the night side and returns below. This circulation can loft particles where air rises. It can clear particles where air sinks. The result is an asymmetric rim. One side can show a thicker haze cap. The other side can show a cleaner, sharper edge. A visual anchor returns to the disk. The day side is not seen as a face, yet its influence appears as a slight bulge in the glow. The bulge is offset downwind. It resembles a gentle swelling in a thin ribbon. The swelling is brightest near a narrow arc. The arc traces where rising air is strongest. Along that arc, the outer veil looks more extended. Along the opposite arc, the veil fades faster into darkness. Another calm payoff settles. Limb asymmetry can indicate circulation direction without any cloud map. The inference remains delicate. Many causes can produce similar shapes. Haze composition can mimic circulation effects. Particle size can mimic temperature effects. This is the limit of observation. The limb is not resolved into a grid. It is a one-dimensional curve around a disk. That curve is an average along the line of sight. Local patches are blended together. A high haze deck can conceal variations below. Refraction can block deeper layers entirely. Even the star's own limb darkening can change the baseline brightness near the edge. These are specific limits. They create degeneracies between scale height haze altitude and particle size. One curve can fit multiple atmospheres. Another small unlock appears in response. Wavelength dependence can separate some of the overlap. If the limb grows thicker, only at shorter wavelengths, fine scattering particles are favoured. If it grows thicker across all wavelengths, a larger scale height is favoured. If absorption notches weaken only when the limb thickens, haze becomes more likely than extra gas alone. Time also helps gently. A stable rim that repeats with orbits suggests long-lived structure. A rim that shifts with stellar activity suggests changing upper layers. The scale shifts again. A particle is smaller than a grain of sand, yet it can brighten a limb that spans thousands of kilometers around a planet. Minutes of vertical mixing can loft particles. Days of circulation can redistribute them around the terminator. Years can change haze supply through slow chemistry. Millions of years can thin an atmosphere through escape. Another visual anchor settles into stillness. The planet drifts as a dark circle. Around it, the thin opal rim remains steady. Its inner edge is bright and clean. Its outer veil is faint and diffuse. In one sector, the rim shows a slight notch where haze is thinner. In another sector, it shows a thicker plume where haze is lofted. These features are not sharp. They are smooth gradients that invite slow attention. A final calm payoff arrives. The limb is not merely an outline. It is a cross-section of climate and chemistry, compressed into a narrow glow. The next section widens from this delicate boundary to the longer forces that reshape whole atmospheres over time as stellar winds and radiation set slow limits on what can remain. The faint rim around a planet can also be the outline of what is slowly leaving. In that region, ultraviolet heating expands the highest air until some of it drifts away over long time. The process begins where the atmosphere becomes thin. The pressure drops. Collisions become rare. Exosphere is the outer air where collisions are uncommon. In that layer, a particle can travel far before meeting another. Its path becomes more like an orbit than a random walk. The first quiet payoff settles. A planet can lose air without storms or eruptions. It can lose it as a steady seep from its most rarefied edge. A visual scene forms at the limb. The dark disk holds steady. Around it, a translucent sheath glows faintly. The sheath is thicker on the warm side. It narrows on the cold side into a sharper boundary. Above the sheath, the glow fades into a long, soft extension away from the star. The extension is not a straight beam. It is a teardrop tail with a rounded head and a tapered end. Its brightness declines by a smooth gradient. The physical detail is clear. A layered edge feeds into a trailing plume. The next checkpoint is heat. Ultraviolet light deposits energy high above the denser layers. Molecules absorb it and break apart. Atoms and ions carry that energy into motion. The upper air warms, warm air expands. Expansion raises the altitude where the atmosphere becomes transparent. Another small payoff settles. Heating in the uppermost layers can reshape what the lower layers do not feel directly. The bulk of the atmosphere can remain calm, yet the edge swells and becomes easier to remove. This swelling changes the apparent size of the planet in a grazing view. It also changes the depth of a dimming event when the planet crosses the star. The band of absorbed light becomes thicker when the upper air is puffier. The story stays quiet because the change is gradual. It can rise and fall with stellar activity and with orbital phase. The main analogy holds steady and unique. The atmosphere behaves like a balloon that loses helium through an invisible pore. The balloon does not pop, it simply becomes subtly less taut over time. Some days the leak seems faster because the balloon warms. Some days it seems slower because it cools. The reason it matters is gentle and direct. A small leak integrated over long time can change the entire feel of the atmosphere. Another visual anchor arrives still slow. The exosphere head is a faint dome above the day side. Its edge is smooth. Its interior is more diffuse. On the night side, the dome blends into a wider halo because particles follow long trajectories before returning. The tail begins not at the surface but above the halo where the star's wind pressure can sweep particles outward. The tail has a central spine that is slightly brighter. Around that spine, a broader fan spreads like a soft veil. The veil is thinnest at the edges. The next payoff settles in the geometry. A tail implies flow. It implies a preferred direction set by the star's wind. Gravity still holds most particles. yet the highest and lightest species can be carried away more easily. Hydrogen escapes first in many cases. It is light and fast. Heavier molecules follow more slowly or they remain behind. This sorting changes composition over time. It also changes chemistry. When hydrogen is lost, water vapor can be indirectly affected. When oxygen remains, it can react with surfaces or with other gases. These are slow consequences. They do not appear as sharp events. They appear as gradual shifts in spectral patterns and in haze formation. A second concept joins quietly without crowding. Photochemistry is chemical change driven by light. Helpfully defined, it is chemistry triggered by high-energy photons. Two gentle examples follow. High-energy light can break a molecule and free reactive fragments. Those fragments can recombine into new molecules that were not stable below. The reason it matters is calm. Photochemistry can create hazes that rise into the upper air and alter escape by changing heating and cooling. Another payoff settles. A haze can both protect and expose. It can block some ultraviolet light and cool layers below. It can also absorb other wavelengths and heat the upper air. The balance depends on particle size and altitude. Fine particles scatter and reflect. Larger particles absorb more. The physical detail stays tangible. A high haze deck can look like a thin cap with a crisp upper boundary. Beneath it, a clearer layer can sit like a gap. Beneath the gap, a denser cloud layer can form a smoother base. Light passing through the limb then encounters a sequence. First a scattering cap, then a clearer window, then a deeper absorbing region. The resulting limb profile can show a bright inner edge and a dim outer veil. The veil can expand during high activity periods and contract during quiet periods. The scale shift turns wide again. A single particle gains energy in a fraction of a second when it absorbs a photon. Yet the atmosphere responds on longer times. It takes hours for heating to spread by motion. It takes days for circulation to redistribute newly formed haze. It takes thousands of years for a steady leak to thin a reservoir measurably. Over about 100 million years, like the time a river can carve a broad valley, the cumulative loss can reshape the entire upper envelope. Another payoff settles in that timescale. A planet does not need a dramatic event to change. It only needs a steady imbalance that persists. The limits of observation arrive softly and specifically. Escape is inferred, not watched directly. The tail is faint and blended with the star's own variability. A signal would appear as extra dimming in ultraviolet wavelengths during a crossing. Yet the same dimming can be mimicked by high haze that blocks light without true escape. A signal would also appear as subtle shifts in infrared absorption. Yet those shifts can be produced by temperature changes rather than composition changes. Even the limb thickness can be ambiguous. A puffier upper air can come from heating. It can also come from lower gravity or higher mean molecular weight changes. These are concrete degeneracies. Several different atmospheres can cast similar silhouettes. The uncertainty is not failure. It clarifies what must be consistent across time and wavelength. Another small payoff settles. When multiple clues agree, the leak becomes more plausible. A thicker ultraviolet limb that varies with stellar activity suggests heating-driven expansion. A persistent downstream tail suggests sweeping by a wind. A muted set of absorption features alongside a thick limb suggests haze in the upper layers. None of these alone is final. Together they narrow the space of explanations. The section returns to the main visual anchor to stabilize tone. The teardrop halo remains faintly luminous. Its head stays rounded above the dayside. Its tapered tail points away and thins into darkness. Along the boundary between halo and tail, a thin ridge of brightness marks where particles are most concentrated. The ridge is a gradient line rather than a sharp edge. It shifts slightly as conditions change, yet it never breaks the calm outline. The next section widens from this slow leak to the deepest timescales, where climate composition and orbital stability settle into long-term balance, and then drift gently toward quieter states. A planet can look steady because its most important motions are slow. In that region, the balance between reflected light and stored heat shapes a climate that changes gently across long cycles. The dark disk remains unresolved, its limb is faint, yet its overall brightness rises and falls with phase. That brightness carries two quiet fingerprints. One fingerprint is reflectivity, the other is the reluctance to change temperature. Light behaves as both illumination and heating in this setting. Albedo is the fraction of light reflected back to space. A higher albedo makes a world look paler at the same phase. A lower albedo makes it look deeper and dimmer. The first small unlock settles. A planet that reflects more light must absorb less, so its day side warms more slowly. The second concept follows without haste. Thermal inertia is resistance to temperature change. High thermal inertia smooths day-to-night swings. Low thermal inertia allows sharper swings. Like snow that lingers in a shaded hollow long after nearby slopes melt a high inertia, surface keeps yesterday's temperature into today. That matters because the phase curve becomes rounder and less peaky. A low inertia surface yields a more pointed curve. It brightens and warms quickly. It cools quickly as the illuminated portion turns away. A visual anchor forms with slow clarity. The planet's limb shows a faint band where haze catches starlight. Beneath that band, the disk is not uniform in tone. A broad, pale cap sits near one pole. Its edge is not a line. It is a gradient that fades into darker terrain. Around mid-latitudes, a thinner belt appears where reflectivity is higher. The belt is slightly offset from the brightest point. It looks like a quiet ring of frost that has begun to retreat. The cap's boundary drifts over time. It moves a little toward the pole in a warmer interval. It creeps back toward the equator in a cooler interval. Another small unlock settles. A moving boundary can reveal seasonal energy balance even when the surface is never resolved into details. The checkpoint moves into what sets those seasons. In a system with two stars, illumination can vary in more than one rhythm. The primary rhythm is the planet's own orbit. A second rhythm comes from the changing geometry of the stars. Their separation and phase can modulate how much light arrives from each direction. These modulations can be gentle, yet they can shift where clouds form. They can shift where haze thickens. They can also shift where ice becomes stable. The result is not a sudden rearrangement. It is a slow breathing of boundaries. A bright cap thins. A darker band expands. The atmosphere responds by altering how much light is scattered back. Scattering remains a quiet player here. Fine particles can brighten the disk without changing the surface. They also cool the surface beneath by reflecting light. Another payoff settles. A high albedo signal can come from ice or from clouds or from haze, and the climate can still be cooler either way. A second visual anchor arrives to keep the rhythm steady. Along the terminator, the limb glow thickens into a soft collar. The collar is brighter on one side. It fades on the other side. The brighter side shows a smoother gradient. The dimmer side shows a sharper edge, as if the haze deck has a cleaner boundary there. The collar suggests a band of high-altitude particles that persists. Beneath it, the phase brightness does not track perfectly with geometric phase. It lags. The peak arrives after the maximum illuminated fraction. That lag is the signature of stored heat. It is a gentle delay, like a stone that stays warm after sunset. The wee is immediate. High thermal inertia shifts the hottest region downwind or downstream of noon. The phase curve therefore becomes a map of delay. Another small unlock settles. A lag indicates that heat is being moved and stored, not merely received and released on the spot. A single number anchors the timescale of that storage without forcing precision. The lag might correspond to about 10 hours, like the slow cooling of a thick rock face after a brief warm day. 10 hours is not long in an orbit, yet it is long compared to radiative adjustment in thin air. This scale shift is calming. It links the microphysics of molecules emitting infrared light to the macroscopic sweep of the planet's day and night. If the lag is larger, the inertia is higher. If the lag is smaller, the surface and air respond faster. The story moves toward deeper time. Over about 1 million years, like the way a fresh crater rim softens into a shallow bowl, a planet can drift between climate states. Volcanic outgassing can add greenhouse gases, weathering can remove them, ice coverage can expand and contract, the albedo can change as the bright area grows. The thermal inertia can change if more of the surface becomes covered by ice or by liquid reservoirs. These changes feed back on temperature. A brightening event cools the planet. Cooling allows more ice. More ice brightens the planet further. The feedback is gentle but persistent. Another payoff settles. Feedbacks do not need speed to be powerful. They need consistency. A new visual anchor keeps the view quiet and concrete. The polar cap shows a scalloped boundary. The scallops are broad. They are like shallow bays in the edge of a frozen sheet. The bays are not carved by tools. They are formed by circulation patterns that distribute heat unevenly. One bay deepens as warm air intrudes. Another bay fills as cold air settles. The boundary remains smooth at small scales, yet it changes at large scales. A clear physical detail holds the scene. The cap's edge is a gradient, not a cliff. It reveals a transition zone where frost becomes patchy and then disappears. The limit of observation arrives softly and specifically. The disk is not resolved into continents, oceans, or distinct cloud cells. The measured brightness is an average over the visible hemisphere. A bright hemisphere can be ice or clouds or haze, and the signal can be similar. Thermal inertia can be high because of a deep atmosphere, or because of a liquid layer, or because of a thick crust that stores heat. The phase lag can be altered by winds. It can also be altered by cloud patterns that reflect light unevenly. These are real degeneracies. Multiple climates can fit the same curve. Another small unlock settles in response. Wavelength dependence can separate some possibilities. Ice reflects strongly at many visible wavelengths. Some hazes reflect more at shorter wavelengths. Thermal emission in infrared carries a different timing than reflected light. If the infrared peak lags more than the reflected peak, heat storage is favoured. If both peaks track tightly, reflectivity changes are favoured. Time also helps. A persistent lag across many orbits suggests inertia. A changing lag suggests variable clouds or episodic haze. The scale shifts outward again. A photon crosses the atmosphere in an instant. A weather pattern can persist for days. A seasonal shift can take years. A geologic adjustment can take millions of years. In that long span, the planet's brightness curve becomes a slow diary. It does not record every detail. It records the broad tendencies of reflection and storage. The closing image settles gently. The planet remains a dark coin against starlight. A pale cap breathes at one pole. A thin collar of haze traces the limb as a soft ring. The phase curve rises and falls with a small delay, implying stored heat that releases slowly. The next section widens further to the system scale, where belts winds and long-term illumination changes set the outer limits of what remains stable and what gradually thins away. A star system carries an invisible weather front as it moves through the galaxy. In that region, a broad bubble of wind surrounds the stars and sets the boundary conditions for every outer world. The early anchor is simple. The outer edge of that bubble decides how much interstellar gas presses inward. It also decides how sharply energetic particles are deflected. A visual scene appears in deep black. Ahead of the moving stars, a faint arc forms like a pale crescent. The arc is widest at the center and thins toward the sides. Its brightness falls away by a smooth gradient. Behind the stars, a dimmer wake stretches out into a long taper. The wake is not a straight line. It is slightly curved and layered as if multiple thin veils overlap. This is the first calm unlock. A system can have a front and a tail even without any visible clouds. The front is a boundary where flows meet. The tail is where the boundary relaxes and streams away. Astrosphere is the bubble of stellar wind surrounding a star system. It expands until it meets the interstellar medium. The interstellar medium is thin gas and dust between stars. When the system moves, the meeting point becomes asymmetric. On the leading side, pressure is higher. On the trailing side, pressure is lower. The bubble, therefore, becomes compressed into a blunt nose and drawn into a long downstream sheath. A second visual anchor settles into detail. The crescent nose has a sharper inner edge and a softer outer glow. Along that inner edge, a thin band appears slightly brighter, like a narrow ridge of light. The ridge marks where the flow changes most quickly. The outer glow is more diffuse. It is where particles begin to slow and mingle. Another small payoff arrives. The shape of the boundary is a record of relative motion. It shows which direction the system is pushing through the surrounding gas. Bow shock is a curved boundary where fast flow slows abruptly. It can form in gas when a supersonic stream meets an obstacle. In this setting, the obstacle is the wind bubble itself. The bow shock is not a solid wall. It is a region where density rises and temperature increases. The rise is not infinite. It is limited by cooling and by the thinness of the gas. The boundary can be broad, not razor-thin. Its thickness is a physical detail that matters. A broader shock makes a softer gradient in brightness. A thinner shock would create a sharper rim. The main analogy holds steady and unique. The boundary behaves like a boulder drifting through powder snow. The boulder does not carve a clean trench. It builds a rounded ridge in front. The ridge has a bright crest where snow piles highest. Farther out, the ridge fades as the powder settles. The Y is immediate. Even in extreme emptiness, repeated collisions can still pile matter into a visible shape when time is long enough. Another payoff settles. The astrosphere sets the pressure at the outskirts of any planetary system. That pressure influences how far a comet reservoir can remain loosely bound. It also influences how dust grains drift and where they are pushed. Small grains feel radiation pressure. They also feel drag from plasma. When the external pressure rises, the outer regions can be more strongly stirred. When it falls, the system can expand and calm. The scale shift remains gentle. A dust grain is smaller than a salt crystal, yet its trajectory can be altered by a boundary that spans billions of kilometers. The motion of the whole system through the galaxy is steady. It can be about 20 kilometers per second, like the fastest gusts of a severe storm multiplied many times. Over a single day, that motion changes little. Over 100,000 years, it carries the stars across a large interstellar neighborhood. This leads to another quiet unlock. The surrounding medium is not uniform. The system can drift into denser wisps and then out again. Each change reshapes the astrosphere. Each reshaping changes how much interstellar neutral gas can penetrate. Charge exchange is when an ion steals an electron from neutral gas. In the outer boundary, stellar wind ions meet neutral hydrogen from interstellar space. An electron swap can create fast neutral atoms. It can also create slower ions that join the flow. This process builds a subtle layer of altered hydrogen near the boundary. It can create a thicker region of neutral gas, often called a hydrogen wall in plain language. The physical image remains calm. The wall is not a barrier. It is a slightly denser shell. Its density rises and falls by gentle gradients. Another visual anchor arrives to keep the rhythm. The crescent nose shows a double edge now. An inner rim is brighter and narrower. A second rim sits farther out and is fainter. Between them lies a dim trough. The trough is not empty. It is simply less emissive. The double edge suggests multiple transition zones. One zone is where the stellar wind slows. Another is where interstellar gas is compressed. Another small payoff settles. Layering at the boundary can reveal multiple physical processes acting at once. The boundary is not a single curve. It is a stack of changes that overlap. These processes matter for atmospheres at large distances. Energetic particles and charged winds can erode upper air. Earlier sections show how heating can swell an exosphere. Here the outer environment controls how hard the wind presses against that swelling. A stronger external pressure can compress a planetary outflow. A weaker pressure can let it extend and escape more easily. The system boundary therefore becomes a slow regulator for long-term loss. Another payoff arrives. A planet can keep more of its light gases during quieter interstellar passages. During denser passages, the same planet can lose more even if the star does not change. The limit of intuition and observation arrives softly and specifically. The astrosphere is not seen as a sharp surface. Its faint arc can be confused with dust emission. Its absorption signatures can be blended with interstellar lines along the same sightline. The boundary shape is inferred from subtle dimming at specific wavelengths. Yet those wavelengths can also be affected by temperature in the surrounding gas. Even the direction of motion can be ambiguous if the medium is turbulent. Models must assume a density and a relative speed. Small changes in either can mimic each other. This is a concrete degeneracy. The same crescent brightness can arise from a denser medium with slower motion, or a thinner medium with faster motion. Another small payoff settles in response. Time variability can help. If the boundary thickness changes slowly while the stars remain stable, external density changes are favoured. If the boundary responds quickly to stellar activity, internal wind changes are favoured. The scale shift widens and then calms. An electron swap happens in less than a heartbeat, yet the boundary position can drift over years. The overall bubble size can adjust over centuries. Over millions of years, the system can pass through multiple clouds with different properties. Those long passages set the broad background against which all shorter climate and escape processes operate. The scene returns to the crescent and tail to end gently. The nose remains a pale arc. Its inner ridge glows a little brighter than the outer veil. The tail stretches away as a layered ribbon that fades into darkness. The whole structure is quiet. It is a large, slow shape drawn by motion through almost nothing. The next section eases from these vast boundaries toward a final stable perspective where the system's signals settle into a calm summary of what endures across time. A star system can be quiet when its strongest clues hide inside soft gradients. In that region, the gradients reveal a stable structure of light and dust through time. Two star disks sit in a field of black. Their limbs fade instead of ending sharply. A pale halo extends outward and thins into darkness. Light is slightly dimmer near each edge, then brighter toward each center. The shading stays smooth. A fine boundary is still sensed within that softness. The disks seem steady, yet the halos show that light does not stop, it blends. The overlap between halo and black is never abrupt. The fade is the first hint of hidden layers. Farther out, a faint band lies in the same plane. It glows as a wide ring of dust. The ring is not uniform. A narrow dark lane crosses its brightest side. The lane has a soft edge. Brightness falls by a gradient, then rises again. A thicker arc brightens on one side as if grains collect there more often. The outer edge fades slowly into black. Within the band, small clumps brighten like low ridges. Other patches look slightly dimmer like shallow troughs. The texture is gentle and slow. It hints at grains sharing similar paths. At this distance, the whole system resembles a tree trunk that stores seasons as rings. Rings do not show leaves. Rings preserve repetition and restraint. Some rings are thin, others are thick. Thickness reflects slow balance over time. The record stays quiet. It still accumulates. Spectral fingerprint means brightness changes across colours of light. The fingerprint repeats whenever the same matter shapes the light. A thin notch in the pattern can point to a specific gas. A gentle tilt across many colours can point to dust scattering. The idea matters because it turns faint light into composition and structure. It allows a quiet signal to carry a layout of materials. The map is not drawn in lines. It is drawn in slopes and small notches. Those shapes persist when many moments are combined. The frame drifts outward from the stellar limbs to the dustband. Dust grains are small. Some are closer to soot specks than to sand, yet together they outline a structure larger than any planet. Gravity shapes the lane without touch. Repeated tugs guide grains away from some paths. Collisions break larger pieces into finer debris. Other collisions let grains stick and grow. The clumps drift along invisible tracks. The tracks are orbits. Over many orbits, a stable arrangement can emerge. A gap can stay clear if a persistent pull keeps sweeping the same region. A bright arc can stay bright if grains linger there. The ring therefore becomes a record of forces, not a set of separate bodies. Here the scale shifts gently. A single grain can respond in a second. A ring responds across years. About 4 light-years separate this system from the nearer dark between stars. The number is like 4 returns of a forest to spring. In the same span, light leaving the ring arrives with its message intact. Distance turns quick flickers into long stories. A brief flare fades away in the stream of photons. A long-lived ring keeps returning as the same soft band. Even the dark lane keeps its place. That persistence is a clue of its own. It suggests structure that outlasts a momentary puff of dust. A planet does not need to be resolved as a disk to leave a mark. A passing silhouette can still shape the combined light. The starlight dips by a small amount, then rises again. The dip is smooth. The dip does not need to be deep. Its consistency matters. Its edges are rounded by haze and by the limb shading of the star. In some colours the dip is a little deeper. In other colours it is slightly shallower. A layered rim is implied by that difference. High haze thins into clearer air. Lower layers become denser and more opaque. Starlight skims through that rim and emerges changed. Light behaves as a filter when it passes through particles. Small particles scatter short wavelengths more strongly. Larger grains scatter more evenly and mute the tilt across colours. The same scattering idea links the planet's rim and the dust ring. One veil is small and curved. The other veil is vast and flat. Both reshape the starlight by the same quiet rules. The scene returns to the ring. The dark lane is still a lane. The bright arc is still a bright arc. The gradients remain smooth. The system keeps imprinting the same shapes in light. A limit appears here, and it is gentle. A single clean curve is not decisive. The curve is still the sum of many layers. It is a limit of inference from blended light. Different mixtures can create similar fingerprints. A thin haze of tiny particles can resemble a thicker layer of larger grains. Cooler air with fewer clouds can resemble warmer air with more haze. The boundary is the inability to choose one mixture from one curve alone. The limit is also one of resolution. A distant signal compresses layers into a single edge. It does not separate one altitude from the next. When several explanations fit, the safest claim is a range rather than a single answer. Time can narrow that range when patterns repeat. When the same dip returns at the same phase structure is more likely. When it shifts or vanishes, transient weather is plausible. The frame eases outward again. The ring fades at its outer edge and darkness thickens beyond it. The stellar halos fade in the same way from bright to pale to nearly nothing. Gradients repeat at every scale. A molecule reshapes light in a tiny way. A dustband reshapes light across a vast span. Over very long spans, the system drifts through a thin interstellar background. That background is not empty. Sparse dust can soften colour slightly and blur contrast. The effect is subtle. It belongs to distance as much as to the system itself. The quiet conclusion settles without strain. Stable structure is found in smooth gradients and persistent gaps. Uncertainty remains, but it stays within clear limits set by the signal. The nearest stars remain a calm anchor in the wider dark. Beyond the ring lies wider darkness. The frame drifts outward without haste.